Okay, ready for the last one? Resistors in parallel. So what we want to do is measure the voltage and current through resistors in parallel. So this is exercise number 5, the last one of this lab. So what I'm going to do is use the same 2 resistors I did before, the smaller resistors, and I put them in parallel. So when I put them in parallel, they have the 2 ends are right below each other, somewhere in the same column. The columns are electrically connected to each other. So this alleviates the use of lots of patch cords. I don't need like 2 more patch cords. If I put them in a breadboard, they're automatically hooked up and they're in parallel. So these are the leads that were left over from the previous exercise. So I'm just going to grab it in like this really carefully. I only need to grab it on one of them because they're electrically connected. Both of the ends are together already. Then I'm going to turn on my power supply. Oh, my ammeter just went to sleep. Hold on. All right, the ammeter has just gone to sleep. Now it's woken up again. So let's go see how much voltage. Oh, geez, my voltmeter also went to sleep. Must time out after like 10 minutes or so. So the total voltage applied to the circuit is 5.039 volts. And the current is pretty high, 0.13, it's flicking, 0.1305, I guess. All right, so that current, 0.130, is split up, some through the top and some through the bottom. They're different resistors, though. So the larger the resistor is going to have less current. The smaller resistor is going to have more current. Now, why is that? Well, the higher the resistance, the harder it is for current to pass through. So it's going to have a lower current. The lower the resistance, the easier that the charge can flow through. So it's going to have a higher current going through it. So the lower the resistor, the higher the current. Again, that's Ohm's law. So the voltage across the whole circuit, again, let's fill out our data table. Then the current to the whole circuit. All right, so then calculate the resistance, the experimental equivalent resistance using Ohm's law. Remember, V equals IR, so to find R, you have to take V divided by R, right? So now let's fill out the table. We're to the table part. The voltage across specific resistor. Well, there's 2 resistors. Let's pick the top one to be number 1 and the bottom one to be number 2. What's the voltage across both of them? Notice how, since both their legs are together on either side, the voltage must be the same. That's the defining characteristic of parallel. So voltage is the same across both of them, but the current is different. Remember, in series, the current was the same, but the voltage was different. Here it's the opposite. The current's different, but the voltage is the same. So the voltage across a specific resistor is the same as the total voltage applied to the circuit, which of course we already wrote down. Oh. Yeah, the reason why it's changing a little bit, you can see it's 5.04, it's moving slightly. It's because these resistors are warming up. So this is an example of error analysis, or a part of the error that can run in. As time goes on, the resistors warm up a little bit, and that will change the current and resistance going in there, the current and voltage, because the resistance itself is changing. Resistance is temperature dependent. These things are getting kind of warm. Whew. It's because they're quite low. It's not like they're 1,000 ohms or something like that. They're 100 ohms and whatever the other one is, 67, whatever the ohmage is. They're fairly low, so there's a lot of current going through there, and they're getting hot, which means the resistance is changing from room temperature value. So you get a slight difference. In fact, let's look what happened just in the, I thought, I did see, oh, there it goes. Now it's 5.041. You see how it's slightly going up? Now the current isn't changing that much though. So now what we're gonna do is I have to somehow figure out how to find the current only through the top one. To do that, I'm going to turn off my power supply. I'm going to change the little alligator clips to the bottom one and pull off the top resistor. I want the ammeter to go in between this lead and the other end of my resistor circuit. So I have to actually figure out which one is the voltmeter. Okay, so the red lead here is the voltmeter. So I'm going to take get this one off and put it on here. All right, so this is the voltmeter lead, so that stays the same. And this is the ammeter. So what I want to do is hook up the power supply directly to the end of this one. So I'm changing around the leads a little bit. The power supply was across the top one. Now I'm making the power supply across this one. Then I'm going to move the ammeter. I'm going to make the ammeter go between these two. So this is the negative end. Now I need one more patch cord to hook between this and that. So it doesn't matter where. I should have like plugged it in better. Okay. So now we're measuring the current only through the top resistor. And the voltage, again, is about the same. Here, you can see the resistance is, the current is quite smaller, 0.053. So that's the current through resistor number 1. Okay? Resistor number 1. Now I'm going to do the same thing, but I'm going to do resistor number 2, or do this a little faster because. So I'm basically going to switch these things. I'm going to put all these things over here and this guy up here. Unfortunately, I don't want it to. Let's see if that works. Yep. All righty. This is not probably the best way to do it, but now the current is 0.078. 0.078, so write that down. That's the current going through resistor number 2. And what I've done is instead of pulling up resistor number 1, I pulled off the end of resistor number 2, and I made the ammeter go from the end of resistor number 2 to the rest of the circuit. I know there's a lot of patch cord stuck in there. So that's basically it. What you do then is on your table, you find the resistance of the specific resistor, that's the fourth column. So you take for number 1, resistor number 1, you take its voltage and current and figure out the resistance for that one. Then for number 2, you got the voltage and current through that one. You find the resistance of that one using Ohm's law. Now, remember, this is for parallel. So resistance in parallel is 1 over R equivalent is 1 over R1 plus 1 over R2. So you just found the resistance of R1 and resistance of R2 using the voltage and current through each resistor. So you're going to plug those values in here. Take 1 over R1 plus 1 over R2. Now that's going to be equal to 1 over R equivalent. So once you get a number over here, you're not quite done. You have to invert it. You have to flip it over to get R equivalent. Then you write that down under the total calculated resistance, right under the data table. Then you find the percent difference with the experimental resistance. So you know the value that you found above the data table? You compare that resistance with the resistance below the data table. Then the next line says sum of currents flowing through the two resistors. The current coming into the circuit, it doesn't disappear. There's something called conservation of charge. So the same current has to come out. So that current is split up. Some of it goes into the bottom resistor, number 2, and some of it goes to the top resistor, number 1. If you add up the current through both resistors, that should equal the total current applied to the whole circuit. So do that now. Add the sum of the currents flowing through each of the two resistors, add them up, and then take the percent difference of those with the total current applied to the whole circuit. And that's it.